Picture this. You've got a massive warehouse-sized supercomputer. It's humming so loudly you literally have to shout over it. Cooling fans are absolutely blasting, and the whole setup is drawing enough electricity to power an entire small city. Now here's the crazy part. Every single time you ask an AI to write an email or explain a tough concept, a warehouse exactly like that kicks into overdrive. It's an uncomfortable truth, really. Our massive pursuit of digital intelligence, well, it's burning through a completely unsustainable amount of physical power.
But let's flip the perspective for a second. Look at this quote. Bill Gates once pointed out something incredibly profound about human intelligence. He noted that all the neurons in our brain, the things that make up our perceptions and emotions, they operate in a strictly binary fashion. Think about it. Our brains are the ultimate computers, yet they run on roughly 20 watts of power. Guys, that's less than a standard light bulb. So it begs the question, if human intelligence boils down to simple binary signals, just on or off, why on earth are our artificial models so mathematically bloated?
Okay, let's dive right into this explainer. What if we actually took a cue from biology? What if we could run these massive language models on almost zero energy? To really grasp how we do that, we first need to feel the sheer mechanical weight of the problem we're facing.
Which brings us to Section 1, AI's energy crisis. It is a massive problem.
See, when you prompt an AI today, it violently shuffles billions of complex decimal numbers around, and that data is heavy. On the left here, we're looking at the old way, 16-bit precision. Imagine a 16-bit number like a massive loaded cargo truck. Now picture 30 billion of those trucks trying to merge onto a clogged highway all at the exact same time. It takes immense infrastructure and massive amounts of fuel. But look over on the right. This is the new way, 1-bit precision. We're literally stripping away the highway. We replace those heavy trucks with a single-track, hyper-efficient bullet train. It's blindingly fast, totally lightweight, and uses almost zero fuel.
So, how do we build that train? Let's move to Section 2, the 1-bit big idea, simplifying AI.
What if we stripped artificial intelligence down to its absolute simplest mathematical form? Just look at how beautifully clean the math becomes here. Standard AI weights are these heavy 16-bit decimals that require grueling multiplication to process. But this new mechanism, it's called BitLinear, throws all of that out the window. It replaces those complex decimals with a simple binary switch. It's just a +1 or a -1. That's it. It's kind of like replacing a messy, oil-leaking mechanical engine with snap-together Lego bricks. You're just adding or subtracting. No heavy lifting required.
And this brilliantly illustrates how that simple concept scales up across an entire system. What you're seeing is the core engine of an AI language model, the attention block. See those BitLinear Lego bricks dropping right into the foundation? They act as a perfect drop-in replacement. You literally just swap out the old energy-draining blocks for our simple +1 -1 switches. Instantly, this massive, heavy architecture becomes incredibly lightweight.
Let's break down the mechanics in Section 3, how BitNet works step by step.
Now, obviously, you can't just delete 99% of a model's brain capacity and still expect it to write beautiful poetry, right? So how does this network, which they call BitNet, actually function? The secret is building it small right from the ground up. Step 1, you binarize the weights. You force the connections to be strictly a +1 or a -1. Step 2, you quantize the activations. So the data flowing between the layers is kept slightly wider at 8 bits, just so the information doesn't choke. But step 3 is where the real magic happens.
Because here's the catch. If everything is just a 1 or a 0, how does the model actually learn those small, delicate nuances during training? Think of it like trying to steer a car where the steering wheel only lets you jerk hard left or hard right. You'd crash immediately, right? Well, the solution is the optimizer trick. Behind the scenes, the model actually keeps a hidden, high-precision ghost weight. It learns smoothly and carefully in high resolution in the background. But when it actually runs the calculations on the surface, it snaps those numbers right back to a simple + or -1. It's this brilliant illusion that preserves the learning process while maximizing efficiency.
Which brings us to the payoff. Section 4, shocking results and massive efficiency.
Now you might be wondering, does a +1 -1 brain actually work in the real world? The answer is absolutely paradigm shifting. 38.8 times. Let's just pause and absorb that number for a second. When scaled up to a massive 30 billion parameter model, this 1-bit architecture reduces the energy cost by almost 39 times. And to be clear, that's not 39%. It takes 39 times less energy to do the exact same thinking.
Now, what's really interesting about this slide is this upward curve. The bottom axis here is the physical size of the AI, while the vertical axis is the energy saved compared to that old 16-bit way. As you can see, as the AI gets bigger and more powerful, the energy savings actually multiply. The larger the brain gets, the relatively cheaper it becomes to run. It's a system that scales perfectly. But here's the million-dollar question. Do we sacrifice intelligence for that efficiency? Take a look at the orange line representing our 1-bit network and compare it to the blue line of the traditional heavy model. The orange line achieves the exact same, and sometimes even better, accuracy. But notice how it's shifted massively to the left in energy consumption. We are getting the exact same intelligence for a tiny fraction of the power. It's a real game changer.
Now, to be fully transparent with you, this isn't totally flawless yet. We're facing two honest limitations right now. First, the data flowing between those connections is still 8-bit. We really need to squeeze those down to 1-bit if we want a truly pure, top-to-bottom binary system. And second, you can't just flip a magic switch on an existing AI. To get these insane benefits, you literally have to spend the time and money to train these models completely from scratch. But those are temporary hurdles. Section 5, the future of small AI, local and efficient.
So, what does our world look like when this technology fully scales? Let's map out the timeline. Today, obviously, AI is completely shackled to power-hungry server farms. But in 5 years, we're likely going to see a massive cost reduction in those data centers, finally reversing the immense drain on our power grids. But look ahead 10 years. Because these models are mathematically tiny, we could run super intelligent language models entirely locally. I'm talking about on your smartwatch, on your phone, working instantly, completely securely, with zero cloud connection required.
All right, let's lock in the main takeaways of this explainer. 1. AI's current massive energy crisis is a total dead end. 2. This 1-bit revolution replaces all that heavy decimal math with simple binary switches. 3. It completely matches the accuracy of traditional models. And 4. It uses a fraction of the energy to do it. We are finally actually building artificial brains that operate a lot more like our own.
So I want to leave you with this final provocative thought. What happens to the world, to our privacy, to our pace of innovation, when a supercomputer-level AI no longer needs a massive supercomputer? What happens when it simply lives, learns, and operates forever, just using the battery of the phone in your pocket? The true intelligence of the future isn't going to be huge. It's going to be invisible.